So let's see questions number 1. In N-channel JFET, what will happen at the pinch of voltage? So the value of VDS at which further increase in VDS will cause no further increase in ID. So if we draw the ID versus VDS, here is the ID, and then the x-axis is the VDX. So typically we have this curve where at these junctions here, this is what we call as the pinch of voltage, right? VDS pinch off. Okay, so now question, the answers A, the value of DS at which further increase in VDS will not cause further increase in ID. So that is correct. So if you increase the VDS here in these directions, the ID never increase. So this answer A is correct. Now if we look to the answers B, the value of VGS at which further increase in VGS will cause no further increase in ID. So definitely this is not the correct answers. So this one, C also is not the correct answers. D also is not a correct answers. Now we see question number 2. A JFET, junction field effect transistor, is a current control device? No. Has a low input resistance? It's not correct. It has a high input resistance. It's a voltage control device? Yes. JFET is a voltage control device. We vary the volt at the gate. We can control the currents flow into the JFET. So the answer is C. Is always forward bias. No, we operate the JFET, which is never forward bias. Okay. So questions number 3, IDSS can be defined as the minimum possible drain current. No. The maximum possible drain current at which the VGS is held at -4 volt. Not correct. The maximum possible drain current with VGS held at 0 volt. Yes, this is the correct answers. Okay. So D, the maximum possible drain current with the shorted. So this is not correct. So what is the majority charge carrier in the base regions of the NPN bipolar junction transistor? So let's say we're going to have this as our symbol to represent this NPN transistor. So this is our base, this is our collectors, this is our emitter. Now the base is made of P-type, NPN, right? It's made of P-type. So the majority charge carrier must be holes. Okay. Number 5, the NPN BJT operate in which mode when the base emitter junction is forward bias and base collector junction is reverse bias? So if we refer to this NPN transistor, okay, so here is our base, this is a collector, this is emitter. Okay, so now base emitter is forward bias. Forward bias means that we're going to turn on the LED, which we know that is 0.7 volt. So this is forward bias. That's why this is correct when we operated in the active region. Base collector is reverse bias. Okay, so this base collector is reverse bias. Okay, so if we want to operate in active regions, base and collector must be reverse bias. So the answer is C. Okay, so answer C. Question number 6. Find the inter-terminal voltage between collector emitters, base emitters, and collector base. Okay, so this is the NPN's transistor. Now we see this is our voltage, base voltage, and this is our emitter voltage, and this is our collector voltage. Okay, so from this case we see, first we assume this transistor is active, and then we find what is the current flow into the base, which is our IB, right? So in that case, we know that the IB is equal to the BVB minus base terminal voltage, then divide the RB. Okay, right. In this case, what is the VB? Remember, if the transistor is active, so VV to VE is 0.7 volt. Now, we know that the emitter voltage is directly connected to the ground, so VE is equal to 0 volt, right? So that means in this case, the base terminal voltage is equal to 0.7 volt. So we're going to substitute this. VVV is supply voltage, 5 volt, minus VV, 0.7 volt, divide RB, 3.9 kilo ohm. So we get the base currents 1.10 milliampere. Okay. Now to find the collector currents, IC is equal to beta IB. So beta is 50 times 1.10 milliampere. So we get the collector currents 55 milliampere. Okay. So we know our IC is 55 milliampere. Okay. Now, so we want to find the VC. VC is equal to VCC minus IC RC. Right. So VCC is equal to 15 volt. So minus IC 55 milliampere times the RC is 180 ohm. Okay, so we calculate this VC is equivalent to 5.1 volt. Okay, so now we have this VC, and then we have the BV, and then we have the VE. So we can find the interterminal voltage. So for VCE, we have VC minus VE. So VC is 5.1 volt minus VE is 0 volt. So VCE is equal to 5.1 volt. Okay, so this is our answers for this interterminal voltage. And then we find interterminal voltage base emitter, which is the VV minus VE. VV is equal to 0.7 volt minus 0 volt. We get 0.7 volt. So that is the interterminal voltage between base and emitter. So last ones, we need to find the interterminal voltage between collector and base, VC minus VV. So VCs, we get 5.1 volt. VV is 0.7 volt. So here we get 4.4 volt. Okay. Okay, now we see these questions. This is a serve bias N channel JFET with the IDSS 40 milliampere, BP 10 volt. Okay, so questions A, what is the value of RS required to serve bias N channel so that we get the VSQ, the Q point, VGS is equal to minus 5 volt. Okay, now for this we need to find what is the ID. Okay, flow in this circuit. The ID flow in this circuit, what you can see here. Let me move this down. Okay, so we have these equations. ID, okay, Q is equal to IDSS 1 minus VGSQ divided by VGS off. Then we take the square of this, right? So given to us, we know VGSQ is equal to minus 5 volts. And so we can write it down. VGSQ equal to minus 5 volt. And then VGS off is equal to minus BP. So BP is equal to 10. Okay. So IDSS also given to us in our questions is equal to 40 milliampere, right? 40 milliampere. So we're going to substitute all these three values into this equation to find what is the IDQ. Okay, so ID as X, we have 40 milliampere. 1 minus VG as Q is minus 5 volt. Then divide by minus 10 volt. And then so we're going to take the square of this. Okay, do these calculations, then the IDQ is equal to 10 milliampere. Okay, so now we know that the IDQ, which is flow from the VDD, okay, go to the ground. This is our IDQ, is equivalent to 10 milliampere. Okay, now in that case, that we know that what is the VG? This VG is directly connected to the ground, is equal to 0 volt. And what is the Vx? What is the Vx? Vx is equal to IDQ RS, right? Okay, so in that case, we know that the IDQ is 10 milliampere, and then we don't know what is RS. To find RS, we need to know what is the Vx, right? So we know that the VGSQ, which is equal to VG minus Vx. Okay, so since the Vg here is equal to 0 volt, so the Vx, okay, so the Vx will be equal to minus VGSQ, which is equal to minus 5 volt, given us here is 5 volt, right? So the Vx we know is 5 volt. Now we know this Vx is 5 volt, we have this ID, and then of course we can find what is the Rx. So the Rs is equal to the Vx divided by IDQ, right? So the Vx is equivalent to 5 volt divided by 10 milliampere. So Rs is 500 ohm. Okay, so that is our answers. Okay. So next, find the value of drain supply voltage that will put a JFET at the edge of ohmic region. So if the JFET will be at the edge at ohmic regions, if it fulfills this equation, that is VDX is equal to VDX PO, right? So what is the VDS PO? VDS PO is equal to BP plus VGS. And from here we know BP is equal to positive 10 volt, equal to positive 10 volt. And then we have this VGS, Q is minus 5 volt. So now we know the VDS-PO is equal to 10 minus 5, we get 5 volt. Okay, so we have these answers on the equations of this, right? Now we need to know what is the VDX, right? So the VDX is equal to VD minus Vx, and that must be equal to 5 volt, right? It's equal to 5 volt. Now, in that case, what we know that is, what is the Vx? Okay, so the Vx we already find out here, which is equivalent to this 5 volt. So Vx is 5 volt here, right? Vx is 5 volt. So we can substitute over here. That means the Vd is equal to 5 volt plus 5 volt. That must be equal to 10 volt. So we know that if this Vd is 10 volt, then it will put a JFET in this at the edge of ohmic region. Now, if you refer to this part over here, okay, what is the VDD that will give us this 10 volt if the ID that flow is 10 milliampere? So this is just a series circuit, right? So the equation for this is we want to find VD. Okay, VD is equal to VDD minus ID RD, right? So we want to find the VDD. So the VDD is equal to VD plus ID RD. So we're going to use these equations to find the VDD. Okay, so now VDD is equal to VD plus ID RD. So we know VD is 10 volt and ID is 10 milliampere. And RD in our case is 700 ohm. Okay, so calculate this, we get 17 volt. Okay, so the supply voltage 17 volt, we put the JFET at the edge of ohmic regions.